name is Mary Kate McGowan. I'm Managing Editor at ASHRAE Journal. Thank you for joining us for today's webinar, part of the ASHRAE Journal Supplier Webinar Series. The series provides information to ASHRAE Journal readers and to others about products and technology of interest to industry professionals. ASHRAE does not review supplier webinar presentations. The following presentation has been prepared by SimScale. The subject is Evaluate the Design, Sizing, and Performance of HVAC Equipment using CFD Analysis. Today's speakers are Hvac Kumar and Richard Surkashula. With a background in aeronautical aerospace engineering and a master's degree in computational engineering, Hvac is a part of SimScale's application engineering team. With a background in applied mathematics and mechanical engineering, Richard is a valuable member of the product management team at SimScale. He and his team constantly try to make SimScale a better fit for every engineer in the world. Richard, the microphone is all yours.
Thank you, Mary Kate, for your warm introduction, and thanks to ASHRAE for having us for today's webinar. Before we start with the actual webinar content, I want to encourage you to ask the Q&A functionality, to ask any questions during the webinar, and we will reserve 10 to 15 minutes at the end for the Q&A session. And as well, if you have any technical difficulties with the sound or anything else, use the same functionality to also ask questions about this, and we'll try to fix it as soon as we can. Today's presentation is about evaluating the design, sizing, and performance of HVAC equipment using CFD analysis. I will present you some common applications that we see with SimScale for the HVAC equipment design, and later Ajit will show you a live presentation of the platform, and you can see how the platform looks like and how you can use it to get design information on HVAC units and equipment, and how we can build better products. First of all, let me introduce SimScale to you, as you might not have heard about us yet. SimScale is a cloud-based simulation tool, and unlike traditional simulation providers, SimScale is cloud-based, and you can open SimScale from any internet-connected device through a traditional web browser. So you don't need any local installation or hardware. At SimScale, our mission is to empower every engineer to innovate faster by making high-fidelity engineering simulation truly accessible from everywhere and at any scale. And we aim for this not only for traditionally simulation-heavy industries like automotive and manufacturing, but also and especially for the built environment, from external wind studies to thermal comfort or air quality assessments. What we have realized at SimScale is that there are three barriers that prevent more engineers and designers to make use of simulation. And the first barrier that we see is the hardware requirement. Traditional software often needs HPC hardware to be purchased by the end user, which is quite cost extensive. With SimScale, there's no specific hardware requirement. You can just use your normal work laptop and a normal web browser. But still, you have the almost unlimited computing capacity that the new cloud technology offers. Additionally, traditional simulation tools have very high fixed costs that occur traditionally at the very beginning of your journey with simulation. With SimScale, we have a very cost-efficient software as a service offering, so you scale up your cost as you also scale up your simulation runs, and you get a better ROI as you go. And last but not least, the know-how barrier is quite high for traditional simulation tools. These tools have been developed since 20, 30 years and were aimed for simulation specialists, people who went through special education, long training sessions to get acquired to the tool, to get used to it and know how it works. SimScale has been developed from the beginning to be easy to use and easily understandable by engineers and designers. Additionally, as SimScale is brought with the browser and through an online interface, we enable seamless collaboration between colleagues that work together on a project, but also between our customers and our support agents. So within the SimScale platform, you have world-class support that is actually live and accessible anytime and there for you whenever you need them. So there's no sharing of any data needed. You can just call the support when you have the project and when you have the problem in the simulation software. Now, traditionally, simulation is done relatively late in the design process. So in the design validation phase, typically. When we broaden the use of simulation to also the designers, we can assess the performance of specific HVAC systems, air handling systems, and so on, directly in the concept phase. That means we can influence the early design definition already and not need to make changes later in the process, where any change is typically much more costly and the changes are only iterative and we cannot make large design changes anymore. Now for today's applications, we will focus on HVAC equipment, the sizing and the design of it. The optimization of HVAC systems usually requires the aerodynamic performance and pressure flow characteristics, which is critical to the overall performance of the HVAC components. Most types of ventilation equipment need to be designed such that they allow a maximum airflow through them while reducing the pressure drop through them. So this can be done by reducing recirculation zones, by adding, for example, guiding vanes in HVAC ducts, or by defining optimal sizings for filters and heating or cooling elements. And we will see that later today how this can be done with SimScale and how our customers have used SimScale to optimize their products. Additionally, in the agenda we see that we'll have the live demo on the platform and the Q&A session, and in the end we'll show you how you can easily get started using SimScale. Now let's have a look at a couple of examples on HVAC products and how they were optimized using SimScale. Here I want to first present to you smart louver technology. On the right side you see their micro louver fabrics, which is an innovative product that has been developed very recently. And it's a solar shading and natural ventilation louver system. And with SimScale, smart louver could assess the performance characteristics of the micro louver screens, such as the discharge coefficients and the solar thermal properties as well. And later, these performance characteristics could be used, for example, in building energy modeling tools, such as IES, TAS, Design Builders, Energy Plus, for the building performance analysis. Also, smart louver could change the design by varying the louver angles, the thickness and spacing of the louvers to find an optimal combination of these design parameters that optimize the airflow through the louver system and still provide the necessary shading capabilities. As another example, on the left side, you see an HVAC unit from our customer Monodroft. And they use SimScale to design and optimize a new generation of net zero hybrid ventilation systems. So with their compact HVAC unit, they can provide natural ventilation, hybrid mixing ventilation, and low energy heat recovery ventilation in a single unit. And with SimScale, they were able to reduce the fan power consumption by 50% by optimizing the air path inside the device to reduce recirculation, pressure drop, and so on. And in the end, reduce the overall power consumption of the HVAC unit, which over the lifetime of the unit has a significant benefit for the actual operator of the HVAC unit when they have it deployed inside their buildings. Additionally, Monodroft was able to assess the compliance with standards such as BB 101 or ISO 7730 for ventilation in schools. And they basically put the HVAC unit itself into a virtual classroom, which allowed them to run a complete study installed in the virtual classroom and ensure that the performance is compliant with the needed regulation standards. And on the right side, what you see is a radial diffuser. Recently, we got a lot of demand for the analysis of air mixing, air exchange rates, and so on in classrooms, but also in office buildings, which is heavily influenced by the choice and the sizing and the design of different diffuser types. So with SimScale, our customers can choose the optimal type of diffuser and the placement and the sizing of the diffusers to ensure they have the required air mixing and air exchange rates in a specific classroom or office room setting. And as a more complex, or maybe not necessarily more complex, but on a larger scale, we can also assess air handling units. So here we are interested in a lot of different parameters. For example, the flow rates through the air handling unit, the pressure drop through the individual components, such as the grills, dampers, the louvers, and in the end, throughout the entire unit. We see that the pressure drop that we generate is dependent on many factors and all the individual components that we have in here. For example, the angles of the louvers, and the choice of the sizing of the different grills, the different dampers, the heating systems, and the cooling systems. Traditionally, each of these components has their own properties, their own fact sheet on the pressure drop through it. For example, for the HEPA filters, which you might need to install more often these days, you have a specific pressure drop. You have the grills, and so on. But the performance characteristics are typically measured and defined on ideal situations. So you have a very constant airflow going through them, and then you will reach the performance characteristics that you get from your data sheet. But what we don't know yet is how will the specific component perform inside the actual air handling unit when you have components before and after it that actually change the airflow pattern in the approaching air that comes into the component. For example, if you have a cooling element and the airflow is very unevenly distributed, you might not get the actual performance out of it because you have a very, very small region with a high flow rate and a large region with a very low flow rate. So with the use of SimScale, we can put all these 20 or more components into the simulation and actually assess how they work together in the actual installation design that we propose. And we can see potential for optimization. As you can see in the lower picture, in the middle region, we have a large recirculation zone, which in general should be avoided. So we can use these insights to change the design of the overall dimensioning of the ducting, for example. We can place, for example, vanes in there to direct the flow more uniformly. And additionally, we can assess the actual cooling performance that we get with this combination. What usually is done is, if you're not really sure if a specific component will be sufficient or not for your situation, it is oversized, right? So fans, the blowers are oversized, the heating and cooling elements are oversized, so we can be sure that they can actually get the required performance in the actual operations. But in today's times, where we aim for net zero buildings, we cannot afford anymore to oversize each individual component. So we need to optimize for minimal energy requirements, minimal embodied carbon, and that's why you need to actually analyze the full system, how each of the components play together to be able to size your system correctly. Not oversize it, but also not undersize it. And then, as a next step, now after we have simulated this air handling unit, what we can also do with SimScale, we can use the results we got from the very detailed, localized CFD analysis and put the results into a larger scale analysis, like a building energy modeling, where you can then, over full standardized year, for example, evaluate the energy needs, for example, or the performance of your system. What we're actually, or what I'm very excited about today is, we just had another webinar an hour before, where we released completely new solver technology with SimScale, which enables very efficient, fast and accurate simulation of rotating machinery equipment, of pumps and fans. With this new technology, we are able to make this type of simulation, which is traditionally very complex and only done by experts, accessible to a very wide audience. We can easily calculate the pressure flow characteristics of any pump design and validate its performance. And what comes into play here as well is the power of the cloud. So already with the new technology that we offer, we can compute the operating point of a pump very fast and accurate. So in this case, the pump simulation took about 15 minutes to compute one operating point. But as SimScale is cloud-based and it uses the actual power of the cloud to have virtually unlimited scalability, what we can also do, if you want to get the full performance curve with 20 data points, this as well just takes 15 minutes, because we can run all the desired simulations in the same time in parallel and get the results as well in 15 minutes. So this is just an example that highlights what becomes feasible with the cloud that might not be feasible today with local simulation hardware and software. And with that, we can directly get over to Ajit for his live presentation of the SimScale platform.
Thanks, Richard, on the wonderful overview of how simulation can be brought into an early stage design to accelerate the process and also to verify the design at a production level. In the next few minutes, we'll take a deeper look into an actual design process of an HVAC equipment and how we can use simulation to evaluate the performance of our product in a real-life scenario. To start with, we can see a list of HVAC components where simulation can be used. Generally, a HVAC system is a combination of two or more functional components to achieve the desired airflow. It can be either a ducting system, where we need to find out how the supply air is distributed over several outlets, or a simple filter system to achieve the required pressure drop and flow characteristics. Simulation can be used to design all these components to work with desired performance. When we think about using these components in an HVAC system, the sizing plays a major role. Can simulation help me determine the sizing as well? Well, the simple answer is yes. To understand this better, we need to step back and see the bigger picture here. So, why are we concerned about the performance of these HVAC products? The ultimate goal here is to achieve a healthy and sustainable environment for all. This is exactly the vision of our host too. So ASHRAE has put a lot of effort over the years in creating valid regulations in the HVAC industry to achieve and create sustainable living conditions. With this background, we can now jump into an actual design process using simulations to develop and evaluate an air handling unit. Let's imagine we have a task of developing an AHU unit. The unit's performance depends upon several parameters like the pressure drop, heating or cooling capacity, and the operating ranges of the blower. We keep in mind these parameters and design a concept that can be used for a wider range of external conditions. That is, the AHU unit that we are going to produce should operate in both summer and winter conditions, and still will be able to achieve the target indoor temperature. Let's assume that we have the concept phase completed. We have the design on hand, and we start focusing on the sizing requirements. In a general workflow, to do this, we need to install the equipment in a given space and see how well it performs. With the simulation, we can easily break down this process into two major levels. One, at the components level, as we have already talked about. So we can take an AHU unit and see how well it performs. What are the outputs that we can get at different parametric conditions? And we can actually use these outputs from this simulation, apply that to a spatial level analysis. We can run several design iterations on the unit and extract the flow condition to be applied at the room level. On a standard building design, we can refer to the sizing regulations to find out the required capacity of the unit at which these units should operate. But what about a scenario where the building design is different from the standard sizing requirements? One good example would be the new regulations that is brought into due to COVID. We now need to make sure we follow the social distancing criteria in the building design and also in designing the HVAC systems. Let's imagine we need to add a separator wall in between the occupants that you see on screen. What happens now with the existing HVAC system? Is it able to cope up with the changes that we made recently? So these are some of the what-if scenarios that can be easily solved or analyzed using simulations. And this is where simulation can actually give us valuable insights. We can easily take the actual model and then modify it and test it for the new conditions or regulations. So this way we can save a lot of time and also get additional insights on what the modifications actually brings into the airflow characteristics. Now, enough talking about where simulation can be used. Let's jump into the tool and see how easy it is to set up and run these kind of simulations. Before jumping onto the tool, I'll again remind the audience to actually ask your questions in the chat so that we can answer them at the end of this session. For beginners with SimScale, so as my colleague Richard mentioned, SimScale is completely a web-based simulation tool. You can access simulation anywhere using a browser and a simple internet connection. So what you see on screen is the browser, and you can log on to simscale.com where you can create an account and start simulating right away. So when you logged into SimScale, you can simply go into your dashboard. So dashboard is where you can actually see all your projects, the projects that you're working on, or you can actually create a new project and start simulating on a different design. For our particular case, we are focusing on the air handling unit. So you can simply open the project in the workbench, and this will take you to the exact simulation setup and also the place where you can analyze your results. Let's take a case where I ran the simulation on this AHU unit and see what are the insights that we can get that might be helpful to increase the performance of this unit, or what kind of results that we can actually collect from this simulation and apply it to the spatial level analysis. So, for example, we go to the solution fields, and here we can derive a lot of quantitative and also qualitative insights from this simulation. So what you see on the screen is the actual results of this simulation, and as we have already known, the AHU unit is already designed to achieve a target indoor temperature at the outlet phase. So we can select the outlet phase to see what is the flow rate at this particular outlet, depending upon the parameters that you have set. So for example, if you're running a summer scenario, the inlet temperature should be at 35 degrees Celsius, and with the temperature difference and the pressure difference, we get about 7.2 meter cube per second of flow rate. So this is already a general input for the spatial level analysis. What you can also check is the target temperature. So we know that we need a target temperature of 21 degrees Celsius at the outlet of this unit. But due to the pressure difference, you can already see there is a variation in the temperature distribution at the outlet. So you can see the minimum at 21 degrees Celsius, and there is also a maximum of 25 degrees Celsius over this phase on the outlet. So this is already a valuable insight on how we can actually improve the model to attain a uniform temperature distribution. So yes, the outlet has a varied temperature over the surface area. And why does that happen? So to take a deeper look into that, we can actually put a simple cutting plane at the midsection of this unit and see what's happening at the outlet. You can already see the placement of the blower and also the sharp angles of the design makes a highly dominant flow on the top section of the air handling unit, and the bottom section is actually subjected to recirculation, and hence there is a temperature difference in the distribution, and also there is a huge variation in flow rate or the velocity of the flow that is coming out of this unit. So these are already some general insights that you can get qualitatively to alter your design to make it like more optimal. One other thing you can also find is how the flow behaves within this unit. So let me switch on the cutting plane and then try to actually animate the wind flow or the airflow inside this particular component. So we will give it a few seconds for the animation to load. But when the animation is loaded, you can actually see how the wind behaves or the air behaves inside this system, which is generally a hard topic to actually find out using a simple prototype approach. So if you have a prototype, you can test it for the performance. You can actually see what is the outlet, what is the inlet, but it's really hard to actually see how the air actually moves within the system. So, for example, you can already see the air from the inlet passes through this pre-filter, and then there is a set of guiding vanes to actually align the wind flow or the airflow through these heating or cooling elements or the other grid systems. One interesting phenomenon that is happening here is because of the angle of the guiding vanes, you can actually see a bit of disturbance or turbulence happening at the lower end of this unit. And this will generate a huge amount of pressure loss, and this pressure loss will actually affect the performance of the system. So as a first design iteration, you can already change the blade angles and see how the wind actually moves within the system. And these are some of the iterations that you can do easily within SimScale or using a simulation. Perfect. Now we have seen what are the results we can get from this unit. As we have mentioned previously in this slide, we're going to take the outlet or the outputs of this simulation and transfer it to a spatial level analysis. So we know the target temperature, and also now we have calculated the flow rate at the outlet. Alright, so we take these two inputs and then apply it to a spatial level analysis here. So for the spatial level analysis, we are considering a regular case with a definite set of occupants inside this room. This room has a glazed window, a Hvac inlet, and a Hvac outlet. So this model also has some of the heating elements within the room, such as the computers or the PCs that generate a little bit amount of heat that might actually affect the comfort of the occupants, and the occupants themselves will be acting as a heating source, because people actually generate a little bit of heat that might actually vary the airflow characteristics and hence the comfort of the occupants. Let's take a look at the results and see how the occupants are feeling inside this room. So the main advantage of actually using SimScale is that you can directly get the thermal comfort parameters as a result in your post-processing. So what you see on the screen is the results on the surfaces mapped with the predicted mean vote. So predicted mean vote is one of the thermal comfort parameters that we can use to judge whether the occupants are thermally comfortable or not. To check this, you can simply inspect any point inside the simulation domain and see what is the predicted mean vote value. So one interesting thing to check here is we need to make sure the thermal comfort is uniformly distributed. So let's see what is the thermal comfort value for the other occupant sitting on the other side. So you can already see there is a bit of difference between the values here. When you actually see it on the other side, it's on 0.15, and here you can already see it's 0.6. So there is a difference in thermal comfort, and you can easily compare these results to a certain set of standards that you can use. For example, if you're using the ASHRAE 55 standards, it actually mentions that the occupants should have a predicted mean vote between -0.5 to 0.5 to consider them as thermally comfortable. So in this case, we're definitely within the range. So it's around like minus 0.6 to 0.6, which means the occupants are thermally comfortable. But what happens if you actually put a separator wall due to the pandemic or the COVID regulations? So these changes can be easily replicated into the geometry, and you can start a different simulation to see whether your Hvac system is able to actually cope up with the changes that you make in the model or in the actual scenario. So this is kind of a general overview of how the simulation looks like, but we can also talk about how we can set up these kind of simulations. So as in all the traditional simulation tools, the simulation starts with actually importing a 3D geometry. So you can simply drag and drop a 3D geometry from any CAD tool. So SimScale supports a huge variety of native formats like SolidWorks, Autodesk Inventor, Rhino, CATIA, and other general formats like STEP, IGES, or STL files. Once when your CAD model is imported into SimScale, you can simply go ahead and create simulation. And this is where you actually select the analysis type for your simulation. So for this particular case, we are interested in the heat transfer or the temperature distribution along with the airflow distribution. So we go ahead with the convective heat transfer, and you can create a simulation. When you click on the Create Simulation button, you can already see a simulation tree on the left-hand side. So from this point on, it's a simple top-down approach where you need to give the inputs for the simulation and then start the simulation. For example, it's going to be really simple. You have the geometry selected, and now you apply the material or the fluid that you want to use. In our case, we use air for the fluid domain, and start focusing on the inputs on the simulation, such as the velocity inlet that we have calculated from the other simulation. So you can give a flow rate and then say it's going to be 0.3 meter cube per second, and also the inlet temperature. So this depends upon the outlet of the AHU unit. So in our case, it's 18 or 21 degrees Celsius. And now you can select the phase for the inlet. You can simply do the same for the outlet. So the outlet is open to the atmospheric conditions at 0 Gauss pressure. And for the other conditions, you can actually create a different set of boundary conditions. I'll simply move ahead and show what we did on the demo case. So we have the inlet, we have the outlet, we have a separate condition for the wall or the window, and we consider the window as a glazed window with a particular ambient temperature at the outlet or the outside and the heat transfer coefficient. We also added certain heating elements such as the PCs and the humans. Once when these physics are set, you're ready to hit the start button for the simulation. So you can go ahead and create a simulation. And when you click on the simulation run, you will get a rough estimation of how much time the simulation is going to take, and also how much computing resources the simulation might require to become simulated. So we'll go ahead and start the simulation. As you remember, SimScale is a completely web-based tool. So whatever simulation or any process that you start is not attached to your hardware. It is entirely going to be running on a separate high-performance computing on cloud. So you can start multiple simulations at the same time. Let's suppose if you want to actually simulate a winter scenario. So the inlet temperature is at 5 degrees Celsius. Then you can simply change this parameter and start a new run. You can rename that as winter and start the run. As you can already see, the runs that we have started have been pushed to the cloud, and they are running in parallel. So by the end of a particular time, you will get the results of all the design iterations or the parametric study that you have started at the same time. This way, you can save a lot of time in actually iterating over your design or verifying your design with different parameters. Perfect. Then this is the top level overview of how to set up a simulation for HVAC systems, but we can get into details on your specific questions. So I'll hand over the presentation to my colleague Richard, and we can focus on some of the questions from the audience right now. Thanks for listening.
Thanks, Ajit, for the nice presentation of the platform. And we can now go on with the Q&A session. Actually, we got a lot of questions, which is great. And I'll pick a few, and then also maybe some can be answered by Ajit. I just go randomly through it. What type of 3D CAD files can be brought into SimScale? I think Ajit has covered this. We can use almost any type of commercial CAD tool. So we can get files in from Revit, from Rhino, SolidWorks, Parasolid, Autodesk, Inventor, CATIA, Creo, Solid Edge, and so on. But also simple files like STL or step files. Then, what else? Can the software be set for imperial units instead of metric? Yes. At the start of a new project, you can define if you want to run it in imperial or in SI units. And also each of the individual inputs that you define, for example, velocity inlet or flow rate, can be also individually selected either for SI unit or imperial unit or something else in between. Take another one for myself and then some for Ajit. Is SimScale able to model wind patterns around buildings? Yes, definitely. This is one of our strongest application fields where we have a dedicated solution where you can run pedestrian wind comfort studies according to specific regulations. So for example, we have implemented the requirements for the City of London wind comfort guidelines. So within SimScale, you can just bring your model of the city, the building, and the surroundings. And within 3 steps, you can set up a fully compliant pedestrian wind comfort study, which then also, as we said before, runs all the different wind directions up to 36 at the same time.
Thanks, Richard. Maybe I can pick a few other questions from the pool. Yeah. So there's a question on what level of physical detail would you need to actually accurately model the grill or a diffuser? So this is actually an interesting question. So it depends upon what kind of analysis that you want to do. If you're into early stage design, what you can do is use a diffuser CAD model. It can be like very detailed, collect the pressure data around it, and then put that into a porous media. So this is what Richard actually mentioned in a case study with our customer for the micro louver, where they wanted to actually do a lot of design iterations. So they analyzed one grill and then collected the data, transferred that into a porous media, and then they made changes on the blade angles and things like that. So you can definitely do like both the spectrums of design detail. Yeah. And there's another question. So can modeling results be ported through XML or similar translation methods to BIM tools or things like that? So this is again an interesting question, because SimScale has also an API, so the application program interface, where you can use that to collect whatever data you require from the simulation that you're running, and then transfer that into any sort of format like XML or CSV file or any other format that is required for the other tools. As Richard mentioned, we can import data into an energy modeling tool like IES or the other tools that you can use with. And there's another question. So would you be able to perform a pipe stress analysis due to high pressure and high temperature? Definitely, yes. So SimScale, as you can see, it has a lot of analysis type under the same workbench, under the same hood. So you have the possibility to actually do fluid characteristics or computational fluid dynamics, as well as some structural analysis like static, dynamic, or harmonic analysis. We do support thermomechanical analysis, which might be the apt solution or the apt analysis type for performing a pipe stress with the temperatures involved. Yep.
Should I take over some more? And you can go over later.
Yeah.
Awesome.
And
so one question is, what type of mesh do you use? The types of mesh vary between the different applications. For example, as you just said, we offer also structural analysis. For this, we use completely tetrahedral meshes. For the outdoor external study, we use hexahedral meshes. It's actually a different type of technology using a lattice-Boltzmann method. And for the indoor CFD analysis, it's a mixed mesh. So we have hexahedral core elements, and close to the walls, we have tetrahedral elements and a layered mesh close to the wall, which is automatically generated. The question is, can ECU model be integrated with room model automatically so that the fan curve for the ECU can be used automatically in the room model? Yes, that can be done. So what we've seen in the ECU unit, the HU unit, is we can define different pressure conditions and get the different flow rates. And there's then a boundary condition that you can apply in the room level analysis, which is a fan curve. And this fan curve will then basically have all the different performance characteristics of the HU unit defined.
Richard, I can take one more question from the audience. So there's a question about what happens to the models once uploaded to the cloud, once the analysis is completed. So that's a good question. So in SimScale, with the professional plan, what you get is a private subscription. So whatever model you upload into a project is only available to the owner of the account. In your case, if you're the professional owner, then only you might be able to actually see the CAD model and operate with it. And after the solution is completed, the model actually stays within the project. It's totally encrypted, but you have the option to actually delete or modify it upon the simulation that you have performed.
Yeah, there's another question. Why is the PMV high on the occupant's legs?
That's a nice question. Yeah, I mean, I did mention while doing this setup, right? So we do have these heat generating elements, which is modeled into the simulation. So right next to the legs, there were like heat generating computers or PCs. So the local temperature there is different than the other temperatures. So this might actually create a difference in the PMV values near the legs.
Yes, then there are questions about accuracy of the simulation, right? So how does it perform to actually real life measurements? We have actually different sets of reports where you can see this. We have our customer case studies where our customers themselves talk about the accuracy of the simulation compared to the measurements. We also have validation cases, which are a mix between more standard, like academic test cases, but also industrial cases. So there's a dedicated site on our website, which has a lot of different validation examples. And I mean, a general word maybe on accuracy of simulation. The accuracy of the simulation is subject to many factors. One of it is actually the software itself, but there are also other factors in there that often play a bigger role in errors than the individual software that is actually used. So inaccuracies in the modeling of the geometry, maybe inaccuracies in the actual performance of the real life system, manufacturing tolerances, and so on.
There's one more interesting question. So the user asked about, like, can we use a passive scaler to calculate the local age of air? So this is something we can also do with the same convective heat transfer. You add the passive scaler and then measure what is the exchange rate of the fresh air coming into the room and going outside. There is a general question about, can we watch the recording if someone has missed the webinar? Yeah, yes, definitely. We will post the recording of the webinar so that you can have the access to watch it later.
There's a question, maybe Ajit, you can answer that. Can the software consider the leakage of a room or the windows? And if yes, how?
That's a good question. I mean, the leakage should be explicitly defined. If you know, like, what is the range or dimensions of the leakage, this can be modeled within the CAD geometry, or you can actually split a face in the CAD geometry, put that as an opening to the external condition so that you can measure the leakage out of it.
Yeah, and in addition to that, you can also model it, for example, with the porous media, that you don't need to model explicitly maybe a small gap, but you have a little thicker element with a specific porosity to it, which then in the end has the same effect as a small air gap, but you might not need to have the high resolution on the meshing for accurately predicting the air loss there.
There's one other interesting question on the wind pressure around the building. Maybe Richard, you can give a little bit insight about that. So the user is asking, can the data be used to model an ideal inlet for a natural ventilation opening?
Yes, that can be done. So we have actually a very interesting customer case study where we did exactly this. So we have a large-scale building where we ran an external wind study with 16 different wind directions, and from that we extracted the pressure coefficients on the facade elements and the openings, and then we did a second analysis on the interior where these pressure coefficients were then used for the internal natural ventilation design and also for the building energy modeling tool. So one use of these external simulations is actually to predict more accurately the pressure coefficients on the facade, taking into account the actual surroundings of the building, which traditionally the building engineering modeling tools don't do. They work more with analytical approximations of the pressure coefficients that cannot really take into account the surrounding buildings. Do users have control over the mesh, Ajit? Maybe for you.
Sure. That's a good question. I mean, with SimScale, what you're trying to do is majorly cut down like the dependence on the mesh. So you can use the default mesh settings for most of the cases, but you do have all the control over the mesh. If you go into the manual mode, you can actually set a region refinement, a surface refinement, or you can put a minimum or maximum edge length of the mesh. So it's totally controllable if you are deep into the meshing.
Is there a size limit for CAD files to be imported? Yeah, virtually not, but practically yes. So I think the file limit is for a compressed file about 1 gigabyte of CAD data. So there is a limit, but in practical sense, if the CAD file is already 1 gigabyte large, we can expect it to be a huge simulation. We could rather think about simplifying maybe the CAD model before uploading it, but about 1 gigabyte it is. And we sometimes have this specifically when we do large-scale outdoor studies, right, where we have the topography as well as the main building and the surrounding buildings modeled. Then sometimes we reach several hundred megabytes of data, but this can be safely imported. Can the radiation heat transfer be considered in the model? Ajit, do you want to answer?
Yeah, sure, I can answer. So the answer is yes. We can actually include a direct radiation where you can select a surface and give the radiation value, or you can also will be able to use the solar radiation feature. So there was a webinar earlier about that, on how to use the solar radiation feature, where you can put a direction of the solar rays and also the direct and diffusive radiation values.
Yeah, or you can define a location and the time and date, and then we automatically compute the orientation of the solar rays and compute the solar heat load and also the surface-to-surface radiation.
Of course. Thanks, Ajit.
Which turbulence models do you have? We have many different models. For example, the standard model we use is K omega SST, but we also have K epsilon models or more advanced LES models in case that's needed. How does the algorithm for the measure determine points of concern? And are you able to control inflation layer thickness? That's a good question. It touches points that Ajit mentioned earlier. By default, the meshing algorithm on SimScale is very automatic, and it's using two sets of inputs for the actual mesh sizing. So first of all, obviously, it uses the CAD model as one input, and the other input is the simulation setup. And based on these two, we derive an optimal setting for the mesh. For example, when you have walls defined as a boundary condition, we add inflation layers to these faces. Whereas if you define an inlet somewhere, we don't add inflation layers. But what we do is, in the direct direction from the inlet extended into the air domain, we add refinements in this direction, because we can expect some high variation in velocities close to that region. And so in this sense, we try to optimize automatically as good as we can based on the physics and the geometry, the automatic meshing. But if you're very experienced or have very specific requirements on your mesh, you can always also define manually layers on the face. You can define how many layers, how thick they are, and on which faces they should be. Also the expansion rate.
All right. Thanks for your questions. I think we covered most of it. We'll be happy to actually answer.
They're coming in more and more. We cannot answer them all.
Yeah, we'll be definitely reaching out to you guys about your questions, and we can have a one-to-one even to discuss about if you have any specific projects in mind or specific requirements from your side. So
one final question that I want to have answered is someone arrived late and asked about the video, the recording of the webinar. Yes, the webinar is being recorded, and we can also share with you then the recording in case you arrived late or would like to have it for your reference. Yes, and that's the last slide for today. The question is, what are the next steps? We have a nice dedicated webinars page on simscale.com/webinars-workshops, where you find all the upcoming but also past webinars, and you can rewatch them or sign up for the new ones. You can also request one-on-one demos if you think SimScale might be interesting to you. You just go to simscale.com and contact us via that, or directly reach us via sales@simscale.com. And with that, thank you again, Ajit, for a nice presentation. Thank you, ASHRAE. And thank you, Mary-Kate, for having us here today. And thanks, everyone that joined us. It was a pleasure doing the webinar. Thank you.
Thanks, everyone.